Hi. In this video, we are going to look at a new section of the course, which is mathematical induction. So induction is basically a proof method by which we prove statements concerning natural numbers or integers. So let's understand what are the basic forms of induction. So the standard form of induction is this. So we say that let P of n be a proposition related to all positive integers. Proposition related to all positive integers. Suppose that first P of 1 is true. This is the foundation. This is the base case of the induction. And secondly, if P of k is true, it implies that P of k plus 1 is also true. This is the induction step. If these two conditions are true, then P of n is true for all positive integers. For all positive integers n. This is the basic form of induction, the most commonly used form of induction. We first establish the base case, and then we go to the induction step, where if P of k is true, it should imply that P of k plus 1 is true, right? If both these two things are correct, then P of n is true for all positive integers n. Now, it could be in some situations that P of n is defined for only on the set n minus, let's say it is not defined from the starting point of the natural numbers, and the first r minus 1 integers are not there in that set. Then we can replace P of 1 with P of r to make the base case. Basically, wherever you have to prove a statement concerning integers, the initial starting point is what is your base case. So if it starts from n is equal to 1, that's fine. If it doesn't start from n is equal to 1, you can take it as n is equal to r, right? So that is the basic form of induction. Then we look at another form of induction, which is known as the jump form of induction. Jump form of induction. So let's see what this is. So again, P of n is a proposition for all positive integers n, and we suppose that first of all, P of 1, P of 2, and so on till P of L are true. All of these statements, P of 1, P of 2 till P of L are true. And the second assumption is, if P of k is true, it implies that P of k plus L is also true. So notice that we are jumping from P of k to P of k plus L, not P of k plus 1. So if this condition is true, and also the first assumption where P proposition is true for all integers 1 to L, then we can say, that P of n is true for all positive integers n. For all positive integers n. So understand what this induction does. It proves the statement for P of 1, P of 2 till P of L, and then it is jumping from P of k to P of k plus L. If these two assumptions are true, then the statement is proved for all L. Finally, we have the strong form of induction. Strong form of induction. We start off in a similar way. We say that P of n is a proposition for all integers proposition for all positive integers n, and then we say that the assumptions for this induction are P of 1 is true, and the second assumption is if P of n, where 1 is less than equal to n is less than equal to k, are true for any positive integer k, for any positive integer k, that implies that P of k plus 1 is also true. That implies that P of k plus 1 is also true. Then P of n is true for all positive integers n. So why is this called the strong form of induction? Here we are saying, not just saying that P of k implies P of k plus 1, which is the regular induction. We are saying that everything lower than k must be true. P of 1, P of 2, P of 3, till P of k. Everything lower than k, if it is true, and that implies that P of k plus 1 is true, then we are saying that P of n is true. So basically, it's a stronger statement. All the statements for k and any integer less than k must be true, and that should imply P of k plus 1 is true. Right? So these three forms of induction we will see now in certain problems. Okay. So let's look at the first one. It says label the prime numbers. Label the prime numbers with ordered numbers. With ordered numbers from the smallest to the largest. From the smallest to the largest. First prime number is represented by 2. Represented by 2. Second prime number by 3, and so on. Second prime number by 3, and so on. Okay. Prove that the nth prime number, and it is Pn is less than 2 power 2 power n. So 2 power 2 power n is the representation of that prime number according to the scheme that we have described. For example, first prime number is 2, second prime number is 3, third prime number is 4. So nth prime number, whatever it will be, is less than 2 power 2 power n. That is what we have to prove, right? So let's establish the base case. So when n is equal to 1, P of 1, which is equal to the first prime number is 2. So P of 1 is 2, is clearly less than 2 power 2 power 1, which is 4, right? So the base case is true, and we'll use the strong form of induction. We'll use strong induction. So we'll assume that the statement here is true for all n. Suppose the proposition is true for all n less than equal to k, right? That is, we can say P of I is less than 2 power 2 power I, where I goes from 1, 2, 3 till k, right? Okay. So we have this statement. So technically we have many statements. P of 1 is less than 2 power 2 power 1. P of 2 is less than 2 power 2 power 2, and so on till P of k is less than 2 power 2 power k, right? Okay. So if we multiply all of these statements, the LHS and the RHS, we should get P1, P2 product till Pk is less than 2 power. We add up the powers, 2 power 1 plus 2 power 2, and so on, 2 power k, right? And that is equal to, if you do this summation, that will be 2 power k plus 1 minus, it will be 2 power k plus 1 minus 1, right? No, it will be 2 pi. So we'll just do it on the next screen. So we have this statement P1, P2 till Pk is less than 2 power 2 power 1 plus 2 power 2 plus 2 power k. And the sum of this is a simple GP. The first term is 2. There are k terms. So 2 power k minus 1 by 2 minus 1. So this is clear. This is 2 power k plus 1 minus 2, right? So this is equal to 2 power k plus 1 minus 2, right? So we have this statement P1, P2 till Pk is less than 2 power k plus 1 minus 2. So we can say that P1, P2, Pk plus 1 is less than equal to 2 power k plus 1 minus 2. Why? Because adding a plus 1 should not change the power, right? Because power will change if you have added 2 probably, right? So that is less than equal to 2 power k plus 1, right? This should be clear. We have just added a plus 1 that should not change the power, but we have still put a equal to sign here. But it is obvious that this number is less than this number, right? So we have a statement now using strong form of induction and the truth of the propositions for P1, P2 till Pk. We have proved that this statement is true. And now we know that since P1, P2 till Pk cannot divide P1, P2, P3 till Pk plus 1, it follows that any prime factor q of P1, P2, Pk plus 1 cannot be either one of P1, P2 till Pk, and therefore must be greater than equal to P of k plus 1, right? So we know that P of k plus 1 is the next prime number. So this any prime factor q of this cannot be these. So it must be either P of k plus 1 or bigger than P of k plus 1. So we have P of k plus 1 is less than equal to q is less than equal to P1, P2 till Pk plus 1 is less than 2 power k plus 1, right? But we actually don't care about these inequalities. We have just now proved that P of k plus 1 is less than this, right? P of k plus 1 is less than 2 power k plus 1, right? So that is the statement P of k plus 1. So we have concluded the induction step right now, and therefore the whole statement is true, and we have P of n must be less than 2 power n for all positive integers n. I hope you understand what we did. We used strong form of induction. We took all the statements from P of 1 to P of k, and after that we just multiplied them to construct the P of k plus 1 statement. And it follows from the fact that this number doesn't have any prime factors from P1 to Pk, right? Okay, let's look at the second question. This is, let ai and bi, where I is equal to 1 to n, be all positive numbers, and let capital A be the sum of I goes ai from 1 to n, and capital B is the sum of all the bi's from 1 to n. We have to prove that summation I goes from 1 to n, small ai bi by ai plus bi is less than equal to ab by a plus b. This is our statement that we have to prove. Now we can confirm that P of 1 and P of 2 are true. I will show you P of 1. P of 2 involves a lot of calculation, but it can be done. So you can try it yourself. So P of 1 is what? When n is equal to 1, we know capital A is simply A1 and capital B is simply B1. So we have to show that A1 B1 by A1 plus B1 is less than capital AB by A plus B, which is, and this is less than equal to, so less than equal to A1 B1 by A1 plus B1, which is obviously true. So P of 1 is true very trivially. P of 2, you have to do some work and some algebra. So I'll just leave that to you. It's just annoying algebra. But you can prove that P of 2 is true. So what we are going to say is that assume that the inequality is true for n is equal to k, right? So we are going to say basically that summation I is equal to 1 to k ai bi by ai plus bi is less than equal to capital AB by A plus B, where A is summation I goes from 1 to k ai and B is summation I goes from 1 to k bi, right? This is the statement that we have assumed, right? Okay, so let's do it on the next screen. So let's try to calculate the sum of this expression from I goes from 1 to k plus 1 for ai bi by ai plus bi. So that should be equal to summation I goes from 1 to k ai bi by ai plus bi plus the last term we have not included in the summation is ak plus 1 bk plus 1 by ak plus 1 bk plus 1, right? And now from the truth of the kth summation, we know that the p of k is true, right? So we know that this summation is less than equal to a dash b dash by a dash plus b dash. So we have put that there. What is a dash b dash? I will just write it down on the side. A dash is obviously the summation of I goes from 1 to k ai and b dash is I goes from 1 to k bi. So this is from the pk statement. We are writing that here. You're using that statement's truth, right? Then we can say that capital A is equal to A dash plus AK plus 1, right? This capital A is what? Capital A is the summation of I goes from 1 to K plus 1 AI, right? And similarly, capital B will be B dash plus BK plus 1, right? So therefore, this statement, right, is a statement of P of 2, right? Think about it. What is P of 2? Proposition 2 states that you have uh, A1 B1 by A1 plus B1 plus A2 B2 by A2 plus B2, right, is less than equal to capital A B by A plus B, where capital A is what? Capital A is A1 plus A2 and capital B is B1 plus B2, right? Now think about it. Here we have A dash B dash by A dash plus B dash, which looks like this, right? And what is A2 B2? A2 B2 should be uh, we know that AK plus 1. Ah, I'll just do it on the next screen. So let me just write it here. So, so far we have this statement, summation of k plus 1 I is equal to 1, AI bi by AI plus bi. We have said that it is less than equal to a dash b dash by a dash plus b dash plus ak plus 1 bk plus 1 by ak plus 1 bk plus 1, right? This is what we have so far. Now, look at the original statement. Original statement was like this: I is equal to 1 to m ai bi by ai plus bi is less than equal to ab by a plus b. This was the p of n statement, p of n. And we have already established that p of 2 is true. What is p of 2 statement looking like? It looks like this: a1 b1 by a1 plus b1 plus a2 b2 by a2 plus b2 is less than equal to capital A B by A plus B, where capital A will be A1 plus A2 and capital B will be B1 plus B2, right? So from P of 2's truth, we have this statement: A1 B1 by A1 plus B1 plus A2 B2 by A2 plus B2 is less than equal to A1 plus A2 B1 plus B2 by A1 plus A2 plus B1 plus B2. This is true because the original proposition is true for n is equal to 1 and n is equal to 2. We have already shown that, right? So can you see here that this is a combination of two terms just like these, two terms like these. So we can say that since P of 2 is true, we can write it as less than equal to A dash plus AK plus 1 into B dash plus BK plus 1 divided by A dash plus AK plus 1 plus B dash plus BK plus 1. We are just using P of 2 here, P of 2. Look at this, or look at this rather. We are just using this proposition to construct this, right? And now we know that A is equal to summation I goes from 1 to k plus 1 of AI, which is equal to A dash plus AK plus 1, right? And similarly, B is equal to B dash plus BK plus 1. So this statement at the end is just less than equal to AB by A plus B, right? Which means that we have proved the statement for P of K plus 1 now is true. So basically, we have assumed the truth of P of 1, P of 2, and we have actually shown P of 1 and P of 2 to be true. And then we have assumed P of K, and from there constructed that P of K plus 1 is true, which basically completes our induction. And the only difference in this induction is that we need the truth of both P of 1 and P of 2 to prove it. Okay. So the base case involves the proof of both the first two smallest numbers, right? Now basically our statement is true for all m, right? Let's go on to the next one. Question number 3. Suppose there is a sequence A1, A2, so on, of positive real numbers, positive reals satisfying for each positive integer k, a of k plus 1 is greater than equal to k times a of k by a of k whole square plus k minus 1. Okay. So this is a statement that is true for each positive integer. We have to prove that for each positive integer, n, which is greater than equal to 2, a1 plus a2 plus an, the sum of all the ai's is greater than equal to n. right? We have to prove this statement. Okay. So this is, let's call this as equation 1. From 1, we can simplify that equation a little. We can say 1 by k plus a of k plus 1. We are taking reciprocal, so it should be less than equal to ak squared plus k minus 1 by ak into k, right? So that implies that k by a of k plus 1 is less than equal to ak plus k minus 1 by ak, right? This is what we are getting so far. And now we can rearrange it to be ak is greater than equal to k by a of k plus 1 minus k minus 1 by a of k. This is the statement that we are getting from 1, right? Now this looks very much like telescoping series. We are getting ak is greater than equal to k by a of k plus 1 minus k minus 1 by a of k. So notice the pattern here. The denominator has subscript k plus 1, then the numerator is k. Similarly, here the subscript is k, numerator is k minus 1. So this definitely fits the pattern of telescoping series summation, right? So if I add up all these terms, suppose I do sum of k goes from 1 to m, a of k, and I write inequalities for k is equal to 1, k is equal to 2 like this, and add it up. What I will get is greater than equal to summation of k is equal to 1 to m, k by a of k plus 1 minus k minus 1 by a of k. And when you calculate this, this comes out to be m by a of n plus 1, right? So basically, we have converted 1 into 2, and our statement 2 is basically summation of k goes from 1 to m, a of k is greater than equal to m by a of n plus 1, right? We have this statement. Now we will use induction, and we'll try to use induction for the proposition of n, which was a1 plus a2 plus an is greater than equal to n, right? When n is equal to 2, right? This was true for n greater than equal to 2. So our base case starts from n is equal to 2, right? When n is equal to 2, we get from equation 1, if we put k is equal to 1, put k is equal to 1 in equation 1, which was 1 by ak plus 1 is less than equal to ak square plus k minus 1 by k ak. So if I put k is equal to 1 here, we get 1 by a2 is less than equal to a1 square plus 1 minus 1 by 1 into a1, which implies 1 by a2 is less than equal to a1, right? So that means that a2 is greater than equal to 1 by a1, which means that a1 plus a2 is greater than equal to a1 plus 1 by a1. Notice we have got this, so we have added a1 on both sides. And since a's and all are all positive, therefore a1 plus 1 by a1 is the sum of two reciprocals, so greater than equal to 2 by amgn, right? So basically we have proved that a1 plus a2 is greater than equal to 2, which is my base case of this proposition, right? Great. So now we have shown that the base case is true, and we will now basically assume that P of n is true for a positive integer n, which is greater than equal to 2, right? For n plus 1, if a of n plus 1 is greater than equal to 1, right? Then what will happen? a1 plus a2 plus an plus an plus 1 will be greater than equal to n plus 1, because this stuff is already greater than equal to n, and if this is greater than 1, we have this is greater than equal to 1, so we establish this, right? But this is what we have to prove, right? P of n plus 1, this is P of n plus 1. So in that case, induction is complete. If an plus 1 is greater than equal to 1, it is very obvious induction. We'll take the other case. If an plus 1 is less than 1, then we have a1 plus a2 plus an plus an plus 1 is greater than equal to uh, okay, so we'll use the inequality 2 here. If you remember, inequality 2 was summation k goes from 1 to m, ak is greater than equal to m by a of m plus 1. So if you put n here, you get summation k goes from 1 to n an should be greater than equal to n by a of n plus 1, right? So this part is greater than n by a of n plus 1 plus n a of n plus 1, right? So we can rewrite it as this is equal to n minus 1 by a of n plus 1 plus 1 by a of n plus 1 plus a of n plus 1, right? So I will do it on the next screen. We'll say a1 plus a2 plus an plus an plus 1 is greater than equal to n by a of n plus 1 plus a of n plus 1, which is equal to n minus 1 by a of n plus 1 plus 1 by a of n plus 1 plus a of n plus 1, right? That is greater than n minus 1 by a of n plus 1 plus 2, because this is the sum of two reciprocals, right? By a and gm, we are getting this. Now, we have already assumed, we assumed a of n plus 1 is less than 1. When we were proving this case, we had assumed this. So if it is less than 1, then we are dividing by something less than 1. So we can say that it is greater than equal to n minus 1 by 1 plus 2. Right? If you divide by something less than 1, that is obviously a bigger number. So here we are saying that since it is greater than, the LHS is greater than a bigger quantity, it is obviously greater than a smaller quantity, right? So it is greater than n plus 1. So we are getting a1 plus a2 till an plus 1 is greater than n plus 1. And we have proved the n plus 1 case in both ways, assuming either an plus 1 is greater than equal to 1 or an plus 1 is less than equal to less than 1. So our induction is complete. And therefore, the statement is true for all n, right? We look at one last problem. Let's look at this one. Question number 4. Prove that there exists an infinite sequence an of positive integers a1 is less than a2 is less than a3 such that a1 square plus a2 square plus an square are perfect squares for all natural numbers n. Now the key point here is to prove the statement P of k implies P of k plus 1, where we are saying that we assume that a1 square plus a2 square plus ak square is a perfect square, and from there we want to prove the fact that the higher term a1 square plus a2 square till ak plus 1 square is also a perfect square, right? So let's assume a1 square plus a2 square plus ak square is equal to x square, and let's assume ak plus 1 square is equal to y square. Then P of k plus 1 basically says find a1 square plus a2 square plus a of k square plus a of k plus 1 square, which is equal to x square plus y square. We need to show that this is also a perfect square. So if the conclusion is true, we need to show that x square plus y square is equal to z square, right? This is looking like a Pythagorean triplet, right? So what we will do is we will strengthen the conclusion. We will strengthen the conclusion by proving that there exists an infinite sequence an of positive integers such that a1 is less than a2 is less than an, such that a1 square plus a2 square plus an square are squares of not just any natural number, but are squares of odd numbers for all n. That there exists a sequence, infinite sequence like this, where this sum is always a square of an odd number. Strengthening the induction statement here, because normally the proof that we wanted was proof that it is perfect square of any natural number n. Now we are saying it's a perfect square of an odd number, right? We are basically making the statement stronger, which is allowed, but in this case, it helps us prove the statement or go from pk to pk plus 1 very easily. So let's try that. So we are saying, suppose the conclusion is true for n is equal to k. Suppose the conclusion is true for n is equal to k. That is, there exists k positive numbers, a1 less than a2 less than a3 and so on less than ak, such that we are saying a1 square plus a2 square plus ak square is the square of an odd natural number. Is 2m plus 1 square for some m belonging to n. Notice now we have strengthened our statement. We are proving it for odd natural numbers, not just any natural numbers. Okay, so we have this statement. Now let's choose a of k plus 1 to be 2m square plus 2m. So we are choosing a of k plus 1 to be 2m square plus 2m. Now, then what will happen to a1 square plus a2 square plus a of k plus 1 square? That will be equal to, this is 2m plus 1 whole square plus 2m square plus 2m whole square, right? So you can show now that this will become equal to 2m square plus 2m plus 1 whole square. Why? Just expand it and you will be able to prove this, which is itself the square of an odd number. Square of an odd number, right? So since a1 is greater than equal to 5 and ak is greater than a1, we have 2 of ak plus 1 is equal to 2 of ak plus 1 is 4m square plus 4m, and which is basically 2m plus 1 whole square minus 1, 2 of ak plus 1. So so basically I'm trying to show that ak is greater than ak plus 1 is greater than ak. That is what I want to show to conclude that my choice was correct. Because already I can say that pk plus 1 is true here. It is the square of an odd number. This number is odd. We just need to prove that this number ak plus 1 fits the sequence, so it must be bigger than ak. So I'm saying 2 of ak plus 1 is 4m square plus 4m, and twice of ak plus 1 will basically be 2m plus 1 whole square minus 1. So we get 2 times ak plus 1 is 2m plus 1 whole square minus 1, which is equal to a1 square plus a2 square plus ak square minus 1. So that is greater than equal to ak square minus 1. That is greater than equal to 2ak, right? AK square minus 1 is greater than equal to 2AK if A1 is greater than equal to 5, right? Correct. So we are getting AK plus 1 is greater than equal to AK. Yeah. So we have shown here that AK plus 1 is equal to 2n square plus 2n is a correct choice if you had assumed A1 square plus A2 square plus AK square is equal to 2m plus 1 whole square. If this is true, if you choose AK plus 1, you have constructed the infinite sequence so that the next term is also fitting the same pattern. Right? The sum of squares of the terms is the perfect square of an odd number. So in this case, we completed the induction by proving a slightly stronger claim from the starting claim. So hopefully you've understood the problem and the other examples before that as well. We'll probably do another class on induction that will be slightly advanced types of induction and concepts of induction. So stay tuned for that. Hope I'll see you next.